Okie doke. So multiband. Yeah, okay, right. Okay, everything loaded up again. Okay, so now we talk about the most commonly used scan on the scanner. So last time in the main lecture I talked about, what did I talk about? I talked about I talked about how grappa works, very common grappa works, and how echoplanar imaging works. So what we're talking about today is one that's even more common now, which is, multiband simultaneous multi-slice, or sometimes called blipped Kuiper or caipirinha. And so this is basically an accelerated way of collecting an EPI scan. And so we're going to talk about how it actually works. It's pretty obscure, and it really requires, it's basically like grappa in many respects. And so we'll try to go through the sequence to sort of get an idea of how, of the little tricks that were done to speed up the acquisition. And so why do people do this? They mainly do it because you can collect data a lot quicker. So you can collect data, you can collect 4 times as much data. So you can typically accelerate your scan by 4 times. And so what do you use this for? Well, one of the things you would use it for, so if you're doing a functional MRI scan, back in the day you could record maybe 15 slices a second, something like that. And if you did a TR2, 15 slices a second gives you about 30 slices, or 26 slices, something like that. And so if you want to get a reasonably good temporal resolution of, say, 2 seconds, then you only got 24 slices. That's not very many slices. It's hard to cover the brain with that. To cover the whole brain, you'd probably have to go up to 3 seconds, 3 or 4 seconds, and then you're sampling relatively poorly in time. So if you can speed up your acquisition by a factor of 4, suddenly then you can do a TR1 with plenty of slices to cover the brain. You could also use, if you're going faster, you could also collect thinner slices, because you can collect, so if we went out to 2 seconds, instead of collecting 3 millimeter slices or 4 millimeter slices, we could collect thinner slices, and so get better spatial resolution. So that was just the ability to go 3 or 4 times faster was irresistible. It could not be resisted by fMRI researchers. They immediately piled into this when this came out about 7 years ago, something like that. And so almost all functional MRI now is done using this method. So we'll just go over it. It's actually, there's not much to it when you first look at it. And basically, what is the plan? You just excite multiple slices. So excite multiple slices. So that seems like reasonably okay, but now the problem is they're all piled on top of each other. So how do we do that? So let's just first draw the pulse sequence. And so the pulse sequence is sort of trivial looking. Basically, you just do multiple frequencies. So here's one frequency, And then you just add another R, because these things are, because the world of MRI is all nice and linear, so you just add another frequency. And you could add a third frequency. So you just add those RF pulses on top of each other. You could slightly move them off to the side a tiny bit to make sure that the peaks don't hit exactly at the same time. But basically, you just pile 3 frequency bands. And so what does that look like? Well, in frequency, that just looks like, 3 frequency bands like that. So, so what does that do? Well, it's on in the context of a slice select pulse. So here we've put on a slice select pulse. And so that's a gradient. So the gradient is on. And so when you, if you put that gradient on, what's going to happen if you feed in 3 frequency bands, it's basically going to select, if this is the x direction, it's going to select 3 slices at the same time, because that will correspond to the 3 frequencies. So here's the 3. There's the 3 frequencies. So you'll select 3 slices in x or whatever. We should make that z. So you'll select 3 slices in z. So if we put our brain in the scanner, so there's the brain in the scanner. So if we put no, that was the x gradient. No, it was the z gradient. So if we put the z gradient on, the z gradient is going this direction in the scanner. And so what will that do? That will basically select 3 slices through the brain like that. 3 horizontal slices. Because those will be the 3. Gosh, can I screw it up anymore? Let's try that one more time. Sorry. Okay, so here's the brain in the scanner. Nice brain. We've put a z gradient on. So there's our z gradient. And what our z gradient is going to do is select 3 horizontal slices. Okay, so it's going to select a slice like that, another one like that, another one like that. So those will be the 3 horizontal slices that correspond to the 3 frequencies that we stimulated the brain with. And so the resonant with the gradient on, the resonant frequency will, excite just 3 slices. So that's the simultaneous multi-slice. So we just stimulate 3 slices. So then what do we do? So this is the GZ, and this is Z. So then we just do a regular echoplanar. So this is exactly the same as a standard echoplanar. So basically, we would go to the corner of k-space in the phase encode direction, and then go to the corner of k-space in the frequency encode direction, and then start, reading out data like this. And then we do a blips like we normally do. So as the readout crosses 0, there's a little blip, and that will slightly move us up 1 line at a time in k-space. And here's another blip. And so that's the big gradient that's going back and forth, and then the echoes come out at the middle. So here's where that's going through the center of k-space each time. So that's all exactly the same The only difference is we just changed our RF pulse to have 3 frequencies in it. So, so now what? So now there's a problem, because if you just collected that data and reconstructed it, what would you get? You would get, so if I just reconstruct that data, so I'm looking at the horizontal slices, I'm looking this way on the horizontal slices, what you would see like, a slice toward the top of the brain, and that would be on top of a slice in the middle of the brain, and that would be on top of a slice through the temporal lobes. So it would just kind of be it'd just be a mess, 3 slices on top of each other. So what was the plan? So the plan was, why don't we just try to move those slices? And so how do we move the slices? So this is a little counterintuitive. We put a Z gradient on, a Z blip. So if we put a little Z blipped, there's the blipped Kuiper. So let's just start out putting on blips that are all the same axis. So here's the regular phase encode blips. So if we put on some additional blips for blipped Kuiper on the Z-axis, what will that do? So this is a little counterintuitive. So this guy is no blips, no GZ blips, no GZ blips. They're just all piled on top of each other. So if we put blips in the Z direction, what is that going to do? It's going to move the slices in the Y direction. So this is GZ blips. So it's going to move things in the Y direction. So why does it do that? So if you think about this, so this is the Z gradient. If you think about that, what it's doing is these blips are adding some phase. They're adding some phase to a whole slice. But the important thing is it's like a phase pedestal. For a given slice. So it means like this slice right here, when this blip hits this slice, it's going to affect all the spins in the slice the same way. So it's going to, if you think about this direction, it's wrapping up spin stripes in the Z direction. But if you just go to one Z point, it's advancing the phase of all the spins in that slice the same way. It's just adding a phase onto the signal coming out of the entire slice. And so that's what I would call it, phase pedestal. So what does that do? So that we haven't talked about it yet, but there's the Fourier. I gave an example of it in the Fourier lectures, but we would call this the Fourier shift theorem. And what this means is if you add a phase to the K-space data, what it does is it shifts image in the image domain. So K-space phase, if we just advance the phase of all the signals in K-space and then reconstruct it, what it will do, it will just shift the image in space. So that's what the the blip does. And so it's, so G blips, so gradient Z blips, it's okay. So gradient Z blips cause image shift in Y direction. Shift in Y direction. Why is it the Y direction? Because the Y direction is the phase encode direction. So shift in phase encode direction. So what does that do to the image? Well, it sort of spreads the image out. So here's the underside of the temporal lobe. Gets down here. It might even wrap around a little bit. Here's the middle image. Then here's the the top image. So it sort of spreads these images out. They'll still be overlapping some. I don't want to say that they're not completely on-overlapping. They're still overlapping. But it will spread them out. Like that. So that's so now we still have a problem. They're still overlapping. So how are we going to deal with that? And we have another problem, which is that if we keep blipping, we're going to really mess up our phase. Because if we keep blipping in the same direction, remember each gradient sort of moves you somewhere in k-space and then leaves you there. So if I keep blipping in the z direction, we're going to get further and further out in z k-space, more spin phase wraps in the z direction, and eventually we'll completely kill our signal. So what do we do? So I describe this as, several different kinds of tricks. So trick number one. So trick number one is, just start with two slices. And let's just say that we only start with a slice right through the zero gradient, where the gradient's not doing anything. So, one at 0, so that's no shift. And then one at, say, like up here, at, at a 180-degree shift. So this is just sort of conceptually working our way through how this complicated thing works. So what we can then do is we can go blip up, blip down. And why can we do that? So we can do that because if we have a 180-degree shift, so this guy is a 180-degree phase shift, and this guy is no phase shift. We remember that 180 degree is the same whether you go plus 180 or minus 180, right? So, minus 180 equals plus 180. So if we blip up and down, then when we go up, we'll get 80, 180. When we get down, we go minus 180. Those are the same. And the one that has no phase shift will also be the same because it's right in the middle. Now that's a little specific. That doesn't seem to help us very much because that's a special case where we just get two slices. And so then sort of conceptually we move along. We say, trick number two is we do the same thing we were doing before with blip up and blip down, but just fix phase before recon. So basically, we could try a slice that was a little offset. It's going to have a phase error in it. Just fix it in k-space. Just rotate all the spins in k-space. before you enter them in k-space, and then that will fix the problem. So just fix the phase before recon. And then there's the, trick number 3. What about, more than 2? So you can do this. You can actually do this. There's a way to do this with more than 2 slices. And basically what you do is, for more than 2, you start off with the very first. You blip down, and then you blip up, and then a bigger blip down. This would be for 3. So I didn't really explain. You can read the original paper to fully understand this, but basically it's yet another trick in order to, with the blips, that allows you to collect 3 slices or 4 slices or even 8 slices. So this is an extensible trick that can be used. The main take-home point is that what you're doing is you need the blips in order to shift the images. We haven't explained why we want to shift the images yet, but you need them to shift the images. But they can't pile up, because it will just kill your signal. And so you have to always do something that's kind of like going back and forth, so that your phase is always basically okay. Okay, so that didn't explain. We still got 3 slices on top of each other. So how do we deal with the 3 slices on top of each other? So the way to think about this now is, what we're basically doing is something like grappa. And so except in the slice direction. So let's draw that out. So just to go back to grappa, which we just dealt with on Wednesday, how does grappa work? So grappa, again, it works by leaving out every other line. If you do grappa 2, so just record every second line of k-space, and then because we've got this effectively k-space blur as a result of our coil having a fall off, there's some information in the other spatial frequencies, and we can use that. Since the information is kind of leaked into other spatial frequencies, we can make a little reconstruction program that looks at those other frequencies and tries to calculate what the missing data is based on actually collecting every line of k-space in the middle of k-space. So the idea was we leave out every other line, but when we get to the middle of k-space, collect every line, and then look at how we can predict the missing data from the surrounding data in k-space. And we can also, one thing I didn't say last time, but it's worth saying, we can do that, for coil 1, and here's coil 2. So we've got 32 coils. So what we can do is we can take the data from another coil. So here's the data, the adjacent data from another coil, and so we're trying to predict one number in k-space, which is here. So let me just do this again. So this is just a quick review of grappa. So we're trying to fill in these missing data points that we didn't collect, and we can use the surrounding data points, but how do we make the predictor that's going to predict the missing data points? And we do that by, say we want to, predict this point in k-space. Then we say, well, we've got 3 surrounding points here, 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 here that we did collect, and we've got the same thing for this coil. And then what we do is we make our single k-space k-space predictor by taking all of these guys. So, all these guys, and then all these guys. So all these guys go into making one prediction for our missing data point. Etc. So not only are we using the adjacent data that we actually did collect, but we're also using all the different coils just to generate one k-space. So there's two things going on. The data's been smeared in space, but then we've got also multiple coils. And so what we can do then is figure out how to predict that number when we've actually collected it from the center of k-space. And then once we have that prediction, apply it to the data where we've left some out. So that was hopefully not stunningly confusing review of how Grappa works within a slice. And so the end result is if you just left out the data from every other line and you reconstructed, what would you get? You would get basically an image that has half the field of view. So if the brain was like this, what's going to happen is this part of the brain here is going to wrap around into the image here, and then this part of the brain is going to wrap around into the image here. So you would have basically the replicas intruding. So that's what would happen if you left out every other line. Now, strangely, when we look at Grappa, when we look at simultaneous multi-slice reconstruction, it's almost the same in a weird way. Let me I'll just draw this guy up here again, so it's a little clearer. So strangely, it's almost the same thing. So here's one slice. We collect data. Normally we collect everything, but if we leave a line out, what happens when we reconstruct it? We end up with this wraparound. So here's the image, but the field of view got half as big, and so the image sort of wraps around like that. So this is FOV. FOV is half as big. And how do we fix that? We fix that by this. So we make a little predictor that uses the surrounding lines in k-space from all the coils to fill in our missing data by training the predictor on all the lines collected. So what happens with simultaneous multiband, multiband simultaneous multislice? It's kind of like we did the following. Our real image was 3 slices like this that are all nice and spread apart. Now, if we recorded all the lines of k-space, then we would be able to get those slices back. But it's as if we left out, we left out, say, we only collected a third of the lines. We left out, every 2 out of every 3 lines. And so what happens when we reconstruct this sort of k-space that is that's undersampled, we get what we actually see on the scanner, which is 3 slices on top of each other. And so what we want to do is just get back here. Just get back to the unoverlapped ones. Now, in real life, we actually collected all the lines. So how can we do this strategy here? Because, we can't go and collect all the lines because we actually did collect all the lines. So, what did we actually collect? We didn't actually collect this. What we actually collected was, all the lines of k-space. Like that. We collected them all. And when we reconstructed them, we got our overlapping slices because there actually were 3 overlapping slices. So what can we do? Well, we can use this additional fact that we've got multiple coils. And so what we can do is take our combined data, but instead of accelerating, collect all the data with a single slice. So not doing the simultaneous multi-slice. So if we start at the beginning of the scan and sort of conceptually, instead of collecting every single line of k-space in order to be able to build the grappa kernel that will fill in our missing data. So this is, these are, grappa kernel to fill in kernel to fill missing data. Instead of doing that, what we do is we collect non-simultaneous multi-slice data. And so once we have that once we have that non-simultaneous data, then we have enough information to do something that's like grappa. So, and we could call it slice grappa. So what are we trying to do? What we're trying to do is basically, call it slice grappa. So regular grappa, we leave out phase encode lines. Versus regular, where we basically, we reconstruct missing phase encode lines. So what we're trying to do here is something different. What we're trying to do here is basically do something of, reconstruct multiple k-spaces for each slice, each overlap slice, yeah. So what we're trying to do is we basically want to take this data, which was fully sampled, later in the scan that has these overlapping slices in it, and what we want to do is like reconstruct 3 k-spaces out of it. So we want to make 3 k-spaces out of it, which means we have to sort of fill in a bunch of data, sort of reconstruct a lot of data. So these are the full k-spaces for each of the overlap slices, which is 3 times as much data as we actually have. And so how do we reconstruct that data? We reconstruct that data in this same sort of grappa-like way, except in the slice domain. And what do we use to construct the effective grappa kernel? We use, make, grappa kernel, or train the grappa kernel using initial non-SMS. So at the beginning of the scan, we don't do the simultaneous multi-slice, so essentially just collect some images that just have one slice at a time. And once we have that data, that data can be used to make the grappa kernel that will allow us to fill in these non-overlap slices and basically generate our 3 non-overlap slices. So yeah, so it's just weirdly like grappa. And that's kind of how it was conceptually developed. So it's the same kind of thing where you're basically interpolating. You're interpolating in k-space, but to do that you need some kind of information that will allow you to interpolate in k-space, and that information comes from the fact that you've got these local coils, and the local coils, you can sort of, another way of thinking of it is when you're scanning through k-space, it's as if you've got like a little filter going through k-space. You have a little blur going through k-space. So when you use a local coil, instead of collecting a k-space point, it sort of collects a little k-space smear. And that basically gives you the information that you need to fill in the missing lines. And we're sort of doing the same thing here, but instead of the phasing code direction, we're doing it in the slice direction. And where we get the extra information from is the adjacent lines in k-space in all these other slices that we collected individually. But the critical thing is it wouldn't work if you didn't have a local coil. So all these things, depend on coil fall off. So coil fall off is a good thing, not a bad thing. So it wouldn't work unless the coil fell off like that. There would be no information in the surrounding points in k-space to use to fill it in. So it requires the coil fall off. So you can see just how these ideas, slowly get twisted around and more complicated. So that's actually how the multiband works. So, and it allows you to go much faster, like 3 or 4 times faster. And that's a really big thing, and so that's why pretty much everybody uses it now. So I think I did a little better than last year. It's still a very confusing thing. I have all the papers. All the papers are online in the readings if you want to go back and look at the original papers on this. So just to sort of explode your mind, you can do regular grappa in addition to multiband. So you could actually just sort of leave out, every other line of your data when you're collecting it, and then fill it in with the regular grappa. So that it's possible to do regular grappa in addition to slice grappa. And that's commonly done. As you start to do this, you can imagine sooner or later, the images start to leak through as you collect less and less data. If you accelerate by a factor of 8, like regular grappa 2, and then collect 4 slice grappa, simultaneously excite 4 slices, and then leave out every other line of k-space when you're collecting that data, you can imagine that you can get into trouble. And I'll talk about that in a later lecture on the kind of artifacts you can get. I mean, you can start to get ghosting artifacts if you do that. Okay, so in the last 5 minutes, we'll talk about another method that is probably going to eventually get more popular, and that is so-called echo volume imaging. So one of the advantages of doing 3D scans, which pretty much every single structural scan now is virtually every single structural scan is a 3D scan. One of the advantages of that is you stimulate the whole brain every time. And so you get more data. You just get a lot more data because instead of just stimulating an individual slice, you're stimulating multiple slices. And so multiple slices, you're stimulating the entire volume. And so what you can do is you can basically do that with echoplanar imaging. So if we do like a 90-degree pulse, or it won't be a 90, it'll be like, say, a 15-degree pulse, because we're doing them so rapidly. And then select the whole volume. So this is the whole volume every time. That's what a 3D scan would do. It would select the whole volume every time. And so, what's going on in K-space? Well, now we've got 3D K-space. So let's try to draw a good 3D K-space. So if this is so if we sort of project those in, here's the center of K-space. So we do our RF pulse. It puts us in the center of K-space, right there. So this is the surface of 3D K-space. So the first thing we do is we go to the 3D corner of K-space. So how do we do that? We just put a phase encode gradient on the slice select line. So here's our go to the 3D corner of K-space. So I'm illustrating this partition direction. This is phase. So that I'm illustrating just a single pulse, the largest negative partition direction phase encode step. And then here we go to the corner of K-space in the Y direction. So this is the Y, here's GZ, RF. And then we go to the corner of K-space in the readout direction. And then we do our regular echoplanar readout. So here's our echoplanar readout, collecting all the lines of K-space. And then here's the blips. That happened. So what does that look like? Well, we go to the corner of K-space, and then we start reading out this K-space. So here we're reading it out, going back and forth like that. So it's like the front face of the cube. We read out all that data, etc. And then when we finished with that, we do the next partition phase encode. And what does that do? That just sort of moves us into K-space a little bit. So here's another slice of K-space. It's not a physical slice of the brain. It's another slice of K-space here. So that's another slice of K-space. And that slightly smaller gradient will then sort of move us over here. And so then we'll do, we'll sort of go back and forth K-space and record all this data in that second plane of K-space. And then we just continue until we've collected all of K-space. So here's the next one. So what's different with the compared to 2D EPI, the only difference is that we select the whole slab every time, and then we do an extra partition gradient. So we're not selecting any slice. So we're collecting, so every single data point comes from the entire brain, and that makes it have a higher signal to noise, because instead of data points only coming from a slice, they come from the entire brain. Now, what's the bad part? So the bad part is basically motion. And the problem is, now what we're doing is we're only reconstructing an image after collecting, say, 1 or 2 seconds of data. So image from, image only reconstructed every 1 to 2 seconds. And so why is that a problem? Well, a very small amount of motion, even from something like breathing, could potentially contaminate the data. Whereas versus, normally when we do EPI, versus single shot, it's called single shot because this is, you can call this one multi-shot EPI, because what happens is you have to do all these different KZ partitions until you get enough data to reconstruct an image. Whereas the single shot, you just do one shot, collect a plane of K-space, reconstruct an image from it, and then that has a much better response to motion, because we're not sort of combining motion across the 1 to 2 seconds. Now, 1 to 2 seconds doesn't seem like very much, but it's enough to cause trouble. And so this, again, this method has been known for a long time, but people haven't done it that much because of some of the motion artifacts. And there's ways to deal with it. So one way, we could use the motion camera. So the motion camera could just track where the person's head was and fix all the gradients so that it will cancel out the motion. So it's a little harder to use that for breathing, although people have even tried to do that for breathing. But basically, this is a higher signal to noise method, and it's especially good for places, especially good for brainstem. Because if you look at a standard, EPI image that's collected with surface coils, small surface coils, the signal to noise here is good, and the signal to noise further away from the coils is less good. And so because of that, this method has a much better signal to noise, because you're hitting the brain with an RF pulse, so here's another RF pulse, another 15-degree RF pulse, but this one's occurring, that TR time is going to be something like, say, like 100 milliseconds. Or even faster. So you're going to be doing 10. You're doing the same number of RF pulses as you would do for slices, except that you're not getting a whole volume until you've done all the RF pulses. Whereas with regular echoplanar imaging, you do an RF pulse, get a slice, another RF pulse, get a slice. So these things are now just partitions instead of actual slices. But the big advantage is you're hitting the brain every time, and so you're getting a much larger signal. It's just physically larger. You just get larger currents in the coils, because protons are emitting from the entire brain, and so your signal is just physically larger, and so that will help you out with parts of the thalamus and the basal ganglia that are in the middle of the brain that are further away from the coil, because here's the actual sort of where the coil would be. And so the signal to noise, it could be on the order of twice as good as you get toward the edge. So it's a big difference. So this is particularly good if you want to do a high resolution image of some deeper part of the brain. So okay, David, I think I've finished we're at the bitter end, so we'll stop here for some questions.